Então, boa tarde a todos e a todas. Estamos aqui reunidos para a defesa de tese de doutorado do Sankhadip Chakraborty. Em todos esses 4 anos, eu nunca disse o seu nome em voz alta, Sankhadip, e agora sabemos por quê. A banca está formada pelos membros do IMPA, eu, Marcelo, Viana, pesquisador Aluno, Lomonaco, pesquisador Khadim War, e pelos nossos colegas Karina, Marin, da UFMG, Lucas Baques, da URGS, Federal do Rio Grande do Sul, e Jiagang Yan, da Universidade Federal Fluminense. Nós vamos dar início à defesa. O candidato dispõe de 50 minutos para apresentar o seu trabalho. Ao final, eu darei a palavra aos membros da banca para a arguição, para perguntas, as quais o candidato irá responder. Terminada a arguição, vamos convidar o candidato a ser retirado da sala de videoconferência e também vamos suspender a transmissão pelo YouTube, que está acontecendo ao vivo. E tão logo a deliberação da banca tenha sido concluída, chamaremos todos de volta para anunciar o resultado. Então, Sankhadip entendeu o procedimento, já está com a sua apresentação na tela, eu dou a palavra, dispõe de 50 minutos a partir de agora.
Okay. So, Marcelo, thank you for your introduction. Let me start by explaining the format of the presentation here. So, I will first talk about the preliminaries, which are partial hyperbolicity, holonomies, Lyapunov exponent, symplectic diffeomorphism, because we'll use some properties of symplectic diffeomorphisms. Then we'll go to the part of motivation, like from where the paper came. That's the part, like it explains what we are trying to do and the invariance principle, which is the basic result that is going to be used. And then there are the results, theorem A, theorem B, corollary C, and theorem D, and that's the end. Okay, let's start. Partial hyperbolicity. So, as always, we are talking about a compact manifold, and a diffeomorphism is said to be partially hyperbolic if there is the tangent space, which is Tn, that admits splitting EU, EC, and ES. These are unstable center and stable directions, which are invariant under the derivative, such that there are some conditions on the norms. And these are some functions, which are pointwise functions. And here, they satisfy some conditions. So the unstable direction is expanded. The stable, when going forward under the actions of f, f squared, f cubed, and so on. The unstable direction is expanded. The stable direction is contracted. And the center direction lies in between. Now, these functions that we have defined here, nu hat, gamma hat, and etc., these will be important in the next definition. So f is called center bunched if these conditions are satisfied. Note that gamma, the function gamma has to do with the center bundle here. So it's a lower bound and upper bound, because the lower bound, the bounds ensure that the center direction does not expand too much or does not contract too much. And this is a condition which relates all the functions that we have mentioned. Okay, so it's a stronger condition than partial hyperbolicity. It strengthens the partial hyperbolicity, and we'll need it later. I will remind you when that time comes. Then there is the question of holonomies. Now I need to go to the board. So what happens is these bundles these two are actually integrable. So we can split the manifolds and split the manifold in foliation that are tangent to the spaces. The foliation tangent to EU is known as, in our, yes, so the foliation tangent to EU in our notation is known as FU. The one tangent to the stable direction is known as FS. And sometimes there is a third one that also exists, which is FC, which is tangent to the central direction. And that does not always exist. When it does, we say that this diffeomorphism is dynamically coherent. Actually, we usually state it differently. We say that when these two are jointly integrable, and when these two are jointly integrable, this is how we state it. And then we take the intersection and find the FC. Okay. Now, then the definition on the board, we define some maps called holonomy maps. So they work like this. We take x and y points in the manifold M. So actually in the first board it was N, here is M. So we take points x, y on the manifold such that the center, we are assuming that the center direction exists. It's dynamically coherent. So the FCX and FCY, FCX denotes the center leaf passing through the point X. So they're contained in the same center stable leaf. And if these homeomorphisms exist, this one here and this one here, we say that the diffeomorphism has global SU holonomies. SU means stable and unstable. This is a short form. So it's kind of like this. So this is, suppose this is a stable leaf. You have X, Y here. And then there are leaves passing through. You have a point, say, X prime. And this is a stable leaf passing through X prime, which is FS X prime. And this point is actually obtained by taking the intersection FS X prime intersection FC Y. And that actually contains a unique point. That's not hard to see. So similarly, we can state this for points X and Y belonging to the same unstable manifold, unstable leaf. Now, a partially hyperbolic diffeomorphism is said to be accessible if any two points can be connected by SU path, some SU path, which means starting from P, you follow either a stable leaf or an unstable leaf. You go to some point, say P1, from there you go to some point P2. So at each turn, there is a choice. You can either choose a stable leaf or an unstable leaf, but it has to be finitely many. And so when any point can be reached from any other point in this way, the diffeomorphism, the partially hyperbolic diffeomorphism, is said to be accessible. Now, the center bunching assumption makes the holonomy C1, and that is a pretty well-known result. I think it can be found in Avila Santa Maria Viana. So when that happens, they can be differentiated, and when they're differentiated, these derivatives DHS xy, DHU xy, they give rise to holonomy maps between the vector spaces. So the first holonomy maps that we defined, they were between the center leaves, and these ones, they are between the vector spaces. So given xy, on the same stable leaf. So these holonomies are from some EC at this point, from EC at that point. Say X prime to the image. And they can be, starting from here, we can actually construct more objects. If we projectivize the center bundle, so the center bundle was like that, EC on N. So we can actually projectivize this bundle, just like we projectivize any vector space. We do it pointwise. If we do that, then the projectivizations of the derivative maps, so they are linear maps, the derivatives, so they can be projectivized as well. They serve as holonomies for the projective bundle. Okay, these are the basic constructions that we are going to need. Now, the Lyapunov exponents. So what is happening here? If this is the Oscillated's theorem, when this map actually taking volume preserving is enough. So when this our map f from n to n is volume preserving, then for almost every p on that manifold, there exists this natural number kp and these numbers, real numbers, lambda 1 to lambda kp, and splitting of the tangent space, which is E1 from E1 to EKP, such that this thing happens. So note that this is clearly related to that expansion and contraction thing we had in the definition of partial hyperbolicity. So when the map is partial hyperbolic, it will show here when we calculate the Lyapunov exponents. It will show here, okay. And these numbers from lambda 1 to lambda kp, these are called the Lyapunov exponents of f at p, and they are. Note that these equalities here, they're strict, but they're strict because we are not counting repetitions. But we can count the multiplicity. Then we get actually n from lambda 1 to lambda n, and we use these little hats to denote that we are actually counting with multiplicity. So the map is said to be non-uniformly hyperbolic if the set of points where the Lyapunov exponents are all non-zero has full volume. Now we go to symplectic diffeomorphism. So given a manifold n, an even dimensional manifold n, in fact, we say omega is a symplectic form if it's closed, which means d omega is 0, and non-degenerate. Okay, and it's clear that this can only exist on even dimensional manifolds. And a diffeomorphism is said to be symplectic if it preserves this symplectic form. And if the dimension of n is 2m, then omega power 2m is clearly a volume form. And if f preserves omega, then omega power m actually, then f has to preserve omega power m as well, so that it's volume preserving. Now we are combining the things we have been defining, Lyapunov exponents and the symplectic diffeomorphism, symplecticity, that diffeomorphism. So what happens is, there is a paper by Viana which discusses this, which is that when you have a partially hyperbolic diffeomorphism and it's symplectic as well, there is a symmetry between the Lyapunov exponents. So the first one and the last one add to 0, the second one and the second to last one add to 0, and so on. And there is more actually. So you can restrict the map to the center leaves. Okay. So it's possible to, you can restrict the form to the central leaf. So this omega c, which is the restriction of omega to the center direction, is non-degenerate, and clearly the closed property is preserved, so it's a symplectic form. And also U plus ES, this is the symplectic orthogonal ECW of the center bundle. Now we are coming to the objects that we are going to study, which are partially hyperbolic skew products with centered dimension 2. So suppose we have a manifold M, compact and everything with that assumed, and there's a transitive Anosov diffeomorphism and CR as well, and S is a compact orientable surface. Then from G0 we define a map F0 from M cross S to M cross S in a way such that it is of this form. So if we fix the base point, which is X, then the action on the leaf, which is the second part, this V goes to lambda X, gamma X V. This depends on the point chosen on the base. That is the definition. And the center bundle coincides with the vertical direction. And we are going to study perturbations of this F0. And what kind of perturbations? We will talk, before we go to the theorems, we will talk about the kind of perturbations we are considering. So we take a CR neighborhood of F0, R is greater than or equal to 2. We take a perturbation there. And it's from normal hyperbolicity theory, which is these particular things are contained in the work of Hugh Pugh-Schub, that invariant manifold books, that F is partially hyperbolic, it is dynamically coherent, and then it has, of course, it has a central foliation FC as well. And this center foliation is close to the original center foliation. Okay, so the leaves are close to the new center leaves are very close to the old center leaves. And the two center foliations are actually conjugate, which means there is a homeomorphism HF from M cross S to M cross S, which maps the leaves of the old foliation to the leaves of the new foliation. Now the invariant principle. So here I have adapted the principle to this particular case we're considering. But the idea of this principle is to study the Lyapunov exponents, and when they have certain properties, like the one given here, which is lambda minus of DCF. By the way, DCF is the restriction of the derivative to the center direction. Okay? We call it the center derivative cocycle, and it has two eigenvalues. Two Lyapunov exponents. One is the smaller one, which is lambda minus, and the other is the bigger one, lambda plus. when they coincide at almost every point, then, and mu is an invariant probability of f, which is Lebesgue, kind of Lebesgue, then it can be disintegrated on the leaves. I will explain what disintegrations are in the next slide. It can be disintegrated in such a manner that the disintegration is bi-invariant. What is bi-invariant? Bi-invariant means invariant under the stable and the unstable holonomies over a full measure bisaturated set. What is bisaturated? So here we are not assuming accessible, but this MF that is shown here, inside this MF, this MF is accessible actually. So we're taking a big set which is accessible. There might be points outside MF that cannot be reached inside from inside MF via SU paths. And if F is accessible, then MF equal to M. So it's a nice nice setting. And as we are going to discuss accessible maps, we will have this. We'll have this MF equal to M. And the conditional probabilities, the so-called the thing we are calling disintegrations, they depend continuously on the base point. And this is the meaning of disintegration. It means, by the way, note that here we are working with the projective fiber bundle, PEC, and also the projectivization of the centered derivative cocycle. So this invariant disintegration means that each MQ is a probability measure on PEC supported on that fiber, and this thing holds. So this is kind of like that, I think it's called Frobenius theorem, which says that you can, so when we evaluate a double integral, dx dy, we can we can first integrate x and then we can integrate y, or we can do the other way as well. So this is an equivalence, this is an analogous result. So we are first integrating this function xi over the leaves separately, and then we are integrating over the whole thing. Now we come to the results. So remember our F naught, which was based on some map G naught on which was on transitive Anosov on some manifold, compact manifold M, and then we took the skew product M cross X, M cross S to M cross S. That was F naught. So that map has a neighborhood U in the space of CR diffeomorphisms, such that if we take an accessible symplectic F in that neighborhood, then it has to satisfy one of the three conditions. So either it is non-uniformly hyperbolic, or the skew product we were talking about over that compact surface S, that surface has to be the torus. And the center bundle contains an invariant continuous line field. What is a line field? Is just a one-dimensional vector bundle. Or it is a line field, or it is an invariant pair of transverse continuous line fields. So this could be a little confusing what this means, because I don't know if this is standard notation, but we'll see what this means when we discuss the proof. So either the first option, which is non-uniformly hyperbolic, or it is a torus, which gives this line field thing, invariant line field thing, or there is a third option as well, which is it's either a sphere or a torus, and there is a continuous Riemannian metric on the central leaves, which is invariant under F and under its stable and unstable holonomies. So what's happening is we are starting, in the proof, what happens in the proof is that we start from the invariance principle. And so invariance principle just gives us the invariant probabilities, the disintegration, right? So we bootstrap that. We start with little information, and we try to see how much more we can get from that little information. So that is what's going to happen here. So first result, the holonomies preserve the symplectic form omega, or in other words, in symbols, this. Okay, and here it's stated in terms of the stable holonomies. It can be stated in terms of the unstable holonomies as well. And that's not very hard to see. I think I should skip this for the time being because I don't have a lot of time left, right? I don't really know. Anyway, so I will explain this if I have time left afterwards. So first result is omega is preserved by the holonomies. Then we have to talk about conformal structures for the second and third part. This is all just lemma. We haven't proved anything yet. So a conformal structure is defined as follows. We take the space of all Riemannian matrix on our surface S, and we consider an equivalence relation. G1 is related to G2 if it's a multiple. G1 is a positive multiple of G2 at some point, at all points. The equivalence classes of this relation are called the conformal structures. And it can be shown that the conformal structures on surfaces are the same as complex structures. Actually, what happens is conformal structures give almost complex structures, and on surfaces, almost complex structures give complex structures. So, yeah, this is a way to get complex manifold structure on the central leaves, because central leaves are modeled after that surface S. And we are still in the lemma phase. Remember, we got from the invariance principle, applying the invariance principle, that version of the invariance principle to our case, we got a disintegration. So a probability measure on each central leaf. Now we are going to use that. So there is a construction of Duodé and Earl, it's referenced at the end, which given this measure on M on PEC, it constructs something called a conformal barycenter BM of EC, and from that conformal barycenter we can construct a conformal structure on EC. Okay. Now this here it is done for C, because EC a priori does not have EC is not C a priori. We have to relate EC and C in some way. So when we are working with C, we consider H, which is the Poincare upper half plane, and delta H when we have a probability measure M on the boundary, delta H, which has no atom of mass half or greater, we can get this conformal barycenter BM, and which is invariant with respect to the conformal automorphisms. It's because the probability measure is okay. No, we don't need it here. Okay, so that's later. So this is just quoting that result from Duarte Earl. We associate to M the unique conformal structure on C, which is preserved with a stabilizer of the conformal barycenter. That is, which is invariant under every linear isomorphism A of this form, such that phi A of Bm is Bm, and phi A is the element of PSL2R. So why? Because the automorphisms of H are of this form. Okay, so maybe this was very fast, so let me go back a little bit. So what is happening is, from the measure, from the disintegration, from the measure, we using Duarte Earl, we are going to the conformal barycenter, which is Bm, and from the conformal barycenter, we are constructing a conformal structure. Remember that the measures are invariant under the dynamics and also invariant under the holonomies. For that reason, the same thing, the same properties, the same invariance holds for the conformal barycenter and the conformal structures as well. Now, alternative 1. Since F is partially hyperbolic, center bunched, dynamic. By the way, the center bunch property is also stable under perturbations. It's dynamically coherent, accessible. It follows that F is ergodic. In particular, the Lyapunov exponents are constant on a full volume subset. If now we restrict our attention to the center Lyapunov exponents. Now, the Lyapunov exponents which are outside, so the first ones, so there is that property. So lambda 1 plus lambda 2m is 0, lambda 2 plus lambda 2m minus 1 is 0. So they occur in pairs. If one is positive, the other has to be negative. So already outside the center bundle EC, we already have kind of a expanding and correspondingly contracting behavior. So we only need to talk about the center manifold, because we don't know exactly what happens there. If we suppose the Lyapunov exponents are lambda negative and lambda minus and lambda plus, lambda minus and lambda plus, the center, these are the center Lyapunov exponents. So if they are non-zero, then one is positive and other is negative, and they're so that gives, when that happens, that gives the first alternative, which is non-uniform hyperbolicity. Okay. And till now, we have not used the invariance principle. Now we are going to use the invariance principle, because we are considering the fact when they are both equal, which in this case means that they are zero, both zero. Now we take any invariant probability measure on the projective center bundle, PEC, that projects to the volume measure. Then from the invariance principle, we are in that situation because lambda minus equal to lambda plus. Then the measure admits a continuous disintegration along the fibers, which is DC invariant because F invariant, and also invariant under the holonomies. Now, suppose it admits a point such that the MP, that probability measure, the conditional measure, admits a mass which is greater than or equal to half. Why we are concerned with this? Because when it's less than half, we can use that, we can construct conformal structures. Before we do that, we have to get rid of the cases where we have masses greater than or equal to half. And as F is accessible and the disintegration is holonomy invariant, it has to be true at every other point, because once you have that mass at one point, it's just carried around everywhere by the holonomies. So at every point, there is a mass, a unique mass, which is greater than equal to half. In our case, we can also have two masses that we consider that later. Now, this gives, note that this measure, this MQ measure, MP in this MQ, this is on PEC. So what we get is, at each point, we get a mass, we get a on each center space, we are getting a line, because projectivization means lines on EC. So it's the set of all lines on EC. So at each point, we are getting a line. And as this atom clearly depends continuously, this is a continuous line bundle. So this line bundle can be either orientable or not orientable. But so we can, when it's orientable, we can use the line bundle to get a vector field on S. And when it is non-orientable, we can go to the orientable double cover. And in the cover, we can get a vector field as well. In both the cases, this can only happen because when the center leaves a tori. This is quite well known, because no other surface supports line fields. We are using the Poincaré-Hopf theorem here. And this was the case where there was a unique atom of mass greater than or equal to half. What happens? We have two. There cannot be more than two, because it's a probability measure. The total measure is half plus half equal to 1. So when we have two, UP and VP, then and they both have masses equal to half. Then we either get a pair of line bundles. When that happens, we can proceed as before, or we can get into a complication, which is we can get two directions which are actually intertwined. So there is no way to say, look, this is the first bundle, this is the center bundle, this is the second bundle. Okay, so when that happens, we do a similar construction. Like we consider cover when to begin with, we assume that these two line fields are intertwined, and when we go to the cover, we just separate them, and we use the same argument. We get a surface which is actually supporting a line field. Again, by the Poincaré-Hopf theorem, that cannot happen unless that surface is actually T2. So in this case, where the conditional measures have masses greater than or equal to half, we get this alternative 2. Now the third alternative is probably the most interesting one, because here we get mode structure. So when there is no atom of mass greater than or equal to half, then we use that conformal structure, that theorem of Duadiol, to get a conformal structure. This conformal structure is continuous and invariant under both the dynamics and the stable and unstable holonomies. And remember that we actually didn't prove, we stated that the symplectic form is invariant under all these things as well. And the conformal structure actually gives an almost complex structure J. So we can use these two things together to get a Riemannian metric, which is pretty standard. This is how the Riemannian metric is constructed. So once we construct the Riemannian metric, we see that it's also invariant under the holonomies and the dynamics as well, because omega and j satisfy those properties. Now, suppose you take one center leaf and, okay, I think I have to take the board. Suppose we have one center leaf and we take a SU path that is coming back to any point. So as the diffeomorphism is transitive, we can just go from any point to any other point. Doesn't matter. So this is the SU path, say gamma, and consider the corresponding holonomy H gamma, which is nothing but the composition of holonomies of each path. So when note that the Riemannian metric is holonomy invariant. So the Riemannian metric is invariant under this H gamma. Okay, so this H gamma is actually an isometry. This means the group of isometries acts transitively on each center leaf, and the center leaves are compact. And that can only happen when the leaf is either a sphere or a torus. So this is the end of the proof of the first theorem, theorem A. Now, this is a point, an interesting point that we need to make. So in the second part, we restrict our attention to when the central leaves are tori. And we also assume, what happened? Okay. We also assume that a certain type of map, this type of map, this thing is accessible. So there can arise a question that can we assume, are there many maps of that form which are accessible? The answer is yes, there are. So every skew product, and this is a more general statement. So every skew product where, remember, we are interested in the case where S is T2. Every skew product where S is a Lie group may be approximated by another skew product over the same base dynamics. So we don't have to change G0. We just perturb a little bit on the leaves, which is stably accessible. Yeah, and this comes from a consideration involving.
Sankhadip, we are still seeing the blackboards. You didn't go back to the PowerPoint.
Sorry. Thank you. So this is okay. We will explain this later if we have time. Okay. So there is a neighborhood UT of F0. F0 is that torus thing in the space of Sear diffeomorphisms, such that every accessible symplectic F in that neighborhood is either non-uniformly hyperbolic. It's the same argument as in theorem A, or the central bundle contains an invariant continuous line field or invariant pair of transverse continuous line fields. Same argument as theorem A. And in this case, there is actually an example where there are actually examples where these things occur. Okay, so it's not easy to get rid of this second option. And in the third case, F is topologically conjugate to an extension of the same form. So we were starting with something F0 looked as xv going to g0 x plus L0 v plus some, oh sorry, this is not plus, this is a comma, some w0 of x. So we started with this. So in this third case, we can conjugate f topologically to a map of almost similar form. So this it is the similar form, a similar form. So this w changes. L naught remains the same, G naught remains the same as well. And here I talk about the first two alternatives. What happens in alternative 3? In alternative 3, as before, we get conformal structures. And as we have each, the leaves, there are the holonomies connect the leaves. Holonomies, one leaf can be reached from another via the holonomies, and the holonomies preserve the conformal structure. It means, and they are also, we will see that the holonomies are actually translations. We'll see the holonomies are actually translations. So, okay, we don't need that right now. Okay, let me go back. So we have holonomies relating the central leaves, and the holonomies are conformal maps because holonomies preserve the conditional probabilities, and from there we can get that they're conformal maps. For this reason, there are many conformal maps between the central leaves. That means they have the same conformal structure. And we can actually, this is an uniformization we do, which is T2 is the torus constructed from C by quotienting by the lattice generated by 1 and tau, where tau is in the upper half plane. Okay. And what we are doing is we are uniformizing each leaf. So we take each leaf, and it is well known that there is some tau that such that suppose we take some leaf FCX, and it is well known that there is some tau such that C. This is the conformally the same. The conformal structure is the same as the one on C quotiented by L1 tau. Now, the point to note here that we can take tau this to be the same for each point, for each central leaf. That's not obvious. So they, of course, they have the same conformal structure because the holonomies are conformal maps. But the nice thing about the nice thing about the torus or complex tori is that there is a certain rigidity. So the conformal maps between complex tori have a certain form, and they cannot be perturbed. We'll see that later. They have conformal maps between tori are rigid, and when we consider different conformal tori belonging to the same class, so suppose we have tau1 and tau2, such that C quotiented by L1 tau1 and C quotiented by L1 tau2. So when we have tau1 and tau2 such that these two tori are conformally equivalent, then tau1 and tau2 has to be related by a discrete group. Okay, so there is a lot of rigidity when talking about tori, complex tori, and that's what finally gives us our result. So, and the second point to note here is that we can. So we are choosing one uniformization for each leaf, right? So it's kind of like choosing a complex coordinate for each leaf, but it's not obvious how that can be done continuously for all leaves. And that's the strength of the result here, because it's a map which is continuous in the first and as well as the second variable, and that we do it by actually solving the Beltrami equation that relates the two conformal structures. Okay. Then the next part says that the stable and the unstable holonomies. Note that now we have some coordinates. So we have complex coordinates on each leaf. Okay? Now we are going to do everything in terms of these complex coordinates. Now, suppose we have a stable holonomy, HSPQ, from the central leaf at P to the central leaf of Q. We can, it's from a torus to some other torus. We can lift this map to look like a map from C to C. Everything is done under the new complex coordinate we have. It has to look like this. Why? Because it's a conformal map from C to itself, and that's how conformal maps from C to itself look. Z goes to APQZ plus alpha PQZ plus beta PQ. And the uniformization map psi is a continuous function of PQZ. That implies that this coefficient is actually depends continuously on the point PQ. And there's a paper which is again referenced at the end by Helfenstein, which actually studies conformal maps, or actually it does in general. It studies holomorphisms between complex tori, and that paper shows that this A alpha here, it cannot be just any alpha. It comes from a discrete set. Okay. Now alpha PQ has to depend continuously on P and Q, but Helfenstein here says that it has to belong to a discrete set. So alpha PQ has to be constant. Now, as P and Q get closer, what happens is the stable holonomy converges to the identity. So as dpq goes to 0, alpha pq has to go to 1. And we have seen before that alpha pq is actually a constant, so alpha pq has to be 1. So once we prove that, it means that each holonomy is actually a translation. The same argument, of course, applies to the unstable holonomies. Now, we just studied the holonomies in terms of our complex coordinates. Now we are starting to we're going to study the map F itself in terms of the complex coordinates. How? Again, we lift it. The lift has to look like, for the same reasons, F has to be a conformal map. The lift has to look like this: AXZ plus BX. Again, AX has to belong to a discrete set, but it has to vary continuously with X. So AX has to be independent of X. So in these coordinates, F has to be of the form, the lift of F has to be of the form some AX plus BX, A times X plus, Z. AZ plus BX. And we can, I'm not going to show the conjugacy explicitly, but this can be, if we go back to the original coordinates, this shows that it is conjugating the F to a map of the form LV plus WX. Now, we do not have much information about A right now. We only know that A is constant, and when we go back to the original coordinates, this A actually gives this L. But remember, we claim that this L is actually equal to L naught. So we have to justify why this L is actually L naught. So what happens is, see, we consider restrictions of F to the center leaves, and the restrictions can be viewed as a map from T2 to T2. Again, we can do this same thing for F naught. So the restrictions can be viewed as map from T2 to itself, T2 to T2. And these leaves, the leaves here in F naught, and the leaves here, I mean the central leaves in F, are uniformly closed, and the maps itself are closed as well. So when we go to homology, they're the same. Okay, so from F, I go to F naught, and F naught actually looks like XV goes to X V plus, sorry, L naught V plus. So we can actually deform this Wx to get rid of it eventually. So in that, what happens is from F we get to F naught, and from F naught we go to L naught. So the action of F on the homotopy on the homology of the torus is actually given by L naught. Now this is in the we have not considered the conjugacy we have constructed using the complex structures. When we go to the conjugacy, we see that F is of the form x comma v goes to x comma lv plus wx. Now in these coordinates, I can do the same thing, and I can say that the conjugacy, the action on homology is actually given by L, and there is a topological conjugacy between this here and this here, because remember we had to use a topological conjugacy to relate F with this particular map here, and which has this particular form, and that conjugacy on the level of homology actually gives a linear conjugacy. So L and L naught must be linearly conjugate, and comparing eigenvalues, we have actually L equal to L naught, because there is something that I think I did not mention. So this L naught here cannot be just anything, because L naught has to preserve the torus, and there are only a few options for L naught actually. And L naught is assumed to be elliptic as well. I think I didn't mention that. Yes. L naught is assumed to be elliptic as well. So there are not many options for L naught. Okay, so in that case, there's a rigidity as well. So once we get a conjugacy like this in L between L and L naught, that means they're the same. Okay.
Sankhadip, we are running a little bit over time, so I suggest you try to wrap it up.
Sure. Okay, fine. Now there's a corollary to this, which this corollary. Remember that there was a second case which gave the line bundles. This corollary actually gets rid of that case. So if L naught, as I told you, L naught is an elliptic transformation. It's a rotation. If we take L naught, and it's a rational rotation actually. So if we take the order of L naught to be greater than 2, then that case does not occur. Okay? And there is a statement D, which is again in the first theorem A. We had a case where the Riemannian, the invariant Riemannian metric case, where the S could be either the sphere or the torus. We already discussed the torus case. What happens in the case of sphere is that the conformal automorphisms of the sphere do not have that rigidity, the rigidity we had for torus. So in that case, we can conjugate. In this case, we get the conformal structure. Using the conformal structure, we do conjugate it to some automorphism. The automorphisms in this case are Möbius extensions. But as there is no rigidity for the conformal automorphisms of the sphere, we do not. So in that case, we got back exactly the L0. We started with L0 V and we got L0 V. In the case of sphere, we do not get that because of that lack of that rigidity. We only get some other Möbius extension which is close to the original Möbius extension, but not the same. Yeah, that's pretty much it.
Okay, thank you very much, Sankhadip. Vamos passar à arguição da banca. A nossa tradição é dar a palavra primeiro a quem vem de longe. Então, eu acho que você, Lucas, seria o primeiro a arguir.
Bom, primeiramente, muito obrigado pelo convite para fazer parte da banca. Em geral, quando você vai ler alguma coisa, né, é bom que essa coisa esteja bem escrita e seja interessante, né? E eu acho que essa tese assim tem essas duas características, né? Tá bem escrita e os resultados eu achei interessantes também. Eu pessoalmente gosto de resultados de classificação, assim, então eu gostei de ler a tese. E bom, eu tenho algumas correções que eu vou te mandar por e-mail depois, então não vou comentá-las agora. Então, mando depois um arquivo com algumas correçõezinhas.
Muito obrigado.
Nada. Enquanto eu estava lendo a tese, assim, eu tive algumas coisas que me vieram na minha cabeça, assim, não sei se fazem muito sentido, mas na sua prova, qual é que é a importância de assumir que teus diffeomorfismos são simpléticos? Essas construções que você faz funcionam todas para diffeomorfismos que preservam volume? Você usa simpléticos só para garantir que os expoentes são simétricos ou em mais algum lugar?
I use it to get the invariant Riemannian metric as well.
Sim, tá. Isso. Então, não tem nenhuma esperança de obter um resultado semelhante a esse no contexto de volume preserving, mas com alguma hipótese, de repente, adicional? Não?
I think so, but not using the same method.
O enunciado do Teorema A, que fala em métrica riemanniana, de fato, como o Sankhadip expôs, na hora que você olha em existência de uma métrica riemanniana invariante, a prova consiste em encontrar uma estrutura conforme invariante. E você já tem de graça uma forma de volume, uma forma de área invariante na direção central. Aí você junta essas duas informações, porque uma estrutura conforme mais uma forma de área dá uma métrica riemanniana. Então você enuncia como métrica riemanniana. Se você aceitar enunciar só como existência de uma estrutura conforme invariante, aí a forma simplética não é necessária. A forma simplética não... Aí, se você aceitar esse enunciado um pouquinho mais pobre, tá? A forma simplética só é usada para a simetria dos expoentes. Tá? Mas como o Sankhadip observou, o enunciado está escrito de forma um pouco mais forte, falando em métrica riemanniana, e métrica riemanniana significa estrutura conforme e forma de área, e forma simplética.
Não sei se seria interessante explorar esse caso volume preserving, talvez não sei.
So what happened was we started with the torus case because we had an idea that torus has some rigidity and stuff. There, I was thinking about this, like getting rid of the symplectic thing and doing something more general. But once we got into theorem A, then we had to drop it.
Uma outra coisa que me veio na cabeça, tipo, suponha que a sua fibra lá seja o toro. E aí no teorema 3, no teorema A, desculpa, você tem 3 possibilidades, né? Ou você é uniformemente hiperbólico, ou então tem aquelas outras duas condições, né? Ou as outras opções. Qual é que é o tamanho do conjunto desses caras que são não uniformemente hiperbólicos nesse contexto? Assim, são densos? Esse conjunto é denso? Não sei se eu me fiz entender direito a pergunta.
Yes. So it's about the zero Lyapunov exponents, right?
Por exemplo, os resultados da Karina, da tese dela, não se aplicariam nesse contexto, eu acho.
Yeah, that's what I was thinking. So we'll have to check results about zero Lyapunov exponents, how well we can remove them and stuff.
Okay, so if eu posso me intrometer na sua pergunta, Lucas. Dos meus comentários era isso ali. Eu acho que você só precisa colocar uma hipótese de center bunching um pouquinho mais forte e você consegue garantir que o não uniformemente hiperbólico é denso lá dentro.
Era o que eu estava imaginando, mas...
Repete o finzinho, Karina, que eu perdi.
Eu acho que é detalhe técnico que eu não verifiquei, mas acho que a hipótese de center bunching você precisa um pouquinho mais forte que no teorema do Sankhadip. Mas se você faz essa mudança, você consegue garantir que o primeiro item no teorema A é CR denso.
Se esse fosse o caso, de repente valeria a pena, né, chamar atenção para esse fato. Eu acho que é interessante, né? E as outras duas condições, elas são meio... Não tem ideia se elas são densas, ou o que elas são, se elas formam um conjunto grande ou não são...
A suspeita é que é um conjunto magro, mas parece que é instável.
In fact, we think in some cases, the second one, that invariant line field, maybe it could be possible to get rid of them under some additional hypothesis. So we didn't get time to explore that.
E aí nessa linha, uma outra pergunta, assim, que talvez não sei se faz muito sentido, por exemplo, o caso 1, de não ser não uniformemente hiperbólico, tem um monte de consequências dinâmicas, né? Já os casos 2 e 3, que tipo de consequências dinâmicas teria, digamos assim? Sei lá, não sei se está bem posta essa pergunta, mas...
Uma maneira de formular, a gente pensou um pouquinho nisso, sim, seria provar a rigidez desses casos aí. Provar que só pode ser da seguinte forma. E a gente tentou um pouco isso, não conseguimos uma conclusão. Mas a ideia aí é que o caso de line fields ou par de line fields deveria ser rígido.
E você comentou, na tese, você comenta um pouquinho sobre a questão da diferenciabilidade da conjugação que você tem, por exemplo, do teorema B, e da função W lá. Você avançou alguma coisa nisso já ou não?
Actually, it can be done when the dimensions are very low. So I think I don't remember very well, unfortunately. I think we did a restriction like ES and EU are both one-dimensional, something like that. The problem with that conjugacy is that it involves that uniformization, and which involves solving the Beltrami equation. So we have to think about the regularity of that equation and then come back. And we actually commented that we can only for now we can only talk about the Helder regularity, not beyond that.
Bom, mas então pelo menos você tem coisa para fazer daqui para adiante, né? Então, parabéns mais uma vez pela tese. Espero que esse seja só o primeiro passo numa carreira de sucesso aí. Parabéns mais uma vez aí. Obrigado pelo convite para fazer parte da Banca.
Muito obrigado, Lucas. E obrigado pela sua disponibilidade na Banca. Eu passo então agora a palavra à Karina.
Obrigada. Tá, primeiramente, também gostaria de agradecer o convite e parabenizar o Sankhadip pela defesa. A gente conversou várias vezes antes, né? Quando ele estava lá sofrendo, então é muito bom ver que você conseguiu, né? Como o Lucas falou, eu acho que a parte que está escrita está bem escrita. Eu tenho só algumas typos, algumas coisas que vou passar depois para você. Mas eu tenho uma reclamação em relação às coisas que você não colocou na tese. Tem muita referência que teria sido muito útil você escrever. Por exemplo, o princípio de invariância você citou aqui, mas na tese ele não está. Então, eu acho que a maioria das pessoas da banca não precisa ler o enunciado, mas seria bom se outras pessoas externas, ou se algum aluno pega a tese para ler, que tudo que você precisa esteja lá dentro, né? Então, tem várias coisas desse tipo, eu posso passar depois para você, mas algumas definições, alguns enunciados que você só cita, mas que seria muito útil que eles estivessem lá na tese mesmo. Aí depois eu posso passar mais em detalhe para vocês ali.
Obrigado.
E eu tenho vários comentários, essencialmente em relação ao enunciado do teorema A. Você fala, por exemplo, que ele tem relação com o teorema do Ávila-Viana, mas que ele é diferente. Você poderia explicar um pouquinho quais são as diferenças?
Mostly the symplectic thing. And they don't talk much about that invariant line. No, they do, but yeah, so this is mostly the symplectic thing. So
because use, they have some structure in the fibers.
Yes.
Yes. So it's not clear for me. Eu empecé a falar em inglês.
Okay.
Está uma confusão. Mas não fica claro para mim qual é a relação ou se não tem relação. Acho que seria bom ser um pouco mais específico sobre isso também. Na tese, né? Porque você só fala é diferente, mas não fica claro quais são as diferenças.
Fine. So I have to write this with com mais calma. So what happened is, as I told you, the focus was theorem B. The focus was always theorem B because we knew that there was going to be rigidity, and then we saw that okay, this can be extended a little bit to get A and C as well. Okay, so that we wrote those afterwards. So B is the best written. Okay, so we'll do that. We'll do that.
Eu acho também, por exemplo, não fica muito claro para mim por que você fixa o mapa F0 no teorema A. De novo, eu entendo que a motivação é o teorema B e o C, né? Mas você poderia provar o teorema A em um conjunto que é uma classe de dífios que verifica tudo o que você quer que verifique, né?
I didn't understand your question.
Você fala, talvez é mais útil, é mais claro se você volta no teorema A na apresentação.
Tá.
Eu acho que na prova você não está usando nada muito específico do mapa F sub 0. Você só precisa que o F seja dinamicamente coerente, center bunches, acessível, dimensão central 2. Eu acho que você poderia anunciar, eu não sei se vale a pena ou se vocês têm interesse, mas eu acho que o mapa F0 aqui no enunciado do teorema A, em princípio, não tem um papel muito importante, né?
So you're saying it does not have to be a skew-product?
Não, porque as conclusões são para o F, né? Você poderia definir um conjunto onde você tem aquele Fibred maps, que são parcialmente hiperbólicos, center bunches, acessíveis, simpléticos, você coloca as hipóteses que você quer. E em todo aquele conjunto, isso aqui é verdadeiro, né?
Isso está certo. Eu acho que esse enunciado foi contaminado pelo teorema B.
Isso, eu entendo que no teorema B, não sei, é claro que você precisa
Você
isso.
tá certo, sim.
Sim.
Mas, de novo, talvez se você quer dar uma intuição para o B, você pode deixar assim também. Não sei se faz muita diferença.
Ok.
Aí, em relação à prova, o único que você precisa é que exista um nesse ou estado, né, para obter o item 2 e o item 3. Então, acho que o item 1 pode ser melhorado fazendo analogia também com o do Viana. Você não só afirma que ele não é uniformemente hiperbólico, mas ele também tem exponentes centrais contínuos.
Ok.
E aí, mesmo se você adiciona as hipóteses ali, vale o mesmo que eu falei para o Lucas, né? Aumentando um pouquinho a propriedade de center bunch, você usa o resultado de minha tese e meus resultados com o Jiagang e você consegue provar que o item 1 é CR denso.
Ok.
Aí eu acho que dá para provar que é aberto e denso, mas a gente não sabe provar isso ainda, né? Mas, pelo menos a densidade você consegue.
Tá.
Eu acho que são comentários que podem ser bons adicionar,
sim.
né?
Poxa,
E tá, eu acho que só isso. Eu vou passar igual depois, né? Tudo escrito para você. Parabéns de novo e muito obrigada pelo convite.
Muito obrigado, Fernando. Qualquer coisa a gente ainda confere com você.
A gente pode marcar uma conversa também, se você quiser, Sankhadip. Vocês só entrar em contato.
Ok.
Muito obrigado. Acho que é Niterói a próxima, Jiagang.
You are muted, by the way, Jiagang.
Okay. Yeah. Thank you first, Marcelo, for the invitation. I'm so happy to see another guy do his defesa thesis speaking English. Yeah, I will speak English. Okay, my Portuguese is bad. So okay, first I would like to say congratulations. I did my defesa also in English. Okay, Marcelo never speak any Portuguese sentence during my period at IMPA.
That's true.
Okay, even nowadays, he only send my email in English.
Yeah, he speaks to me in English as well.
Yeah, he sends the title, Dear Jiagang, best, and I send email to him, Dear Marcelo, best. Okay, quite official.
Yeah.
Okay, so yeah, I on this paper, so I like this paper very much because I never understand very well about the conformal structure. I have been referring over several papers about the conformal structure. So I have no questions. I have only 3 comments. So first, for the theorem A, I think the whole paper you consider the conformal structure for dimension 2.
Okay.
I'm not sure if you have read the paper of Xu and Butler.
I couldn't understand you. Could you please repeat?
Okay, so Butler and Xu. Butler is a student of Amy, and Xu is a student of Arthur Avila.
Okay.
They considered perturbation of higher dimension geodesic hyperbolic geodesic flow. The time 1 map, they get a kind of rigidity. When all the perturbation of time 1 map, you get a diffeomorphism. But if the center, all these exponents of the diffeomorphism coincide with the flows, and then they get some kind of rigidity. In that paper, they consider conform structure for higher dimension.
For higher dimensions?
Yes.
Okay.
So maybe I think in theorem A, maybe you can put some corollary, not so beautiful, but you could put some corollary if the center bundle, if all these burdens are 0, and then you can get some kind of classification.
Okay.
Theorem A, I mean, maybe you could consider a higher dimension with some conform structure. Okay. It's not so complete classification like theorem A, but I think it's interesting.
Could you please send me the name of the paper later?
Okay, Master, I know that. And no, it's okay. So okay, yeah, I will send you later. And another comment is about the corollary C. These corollary C, because all these other papers, you consider F0 and you consider its perturbation, and you see the perturbation if it's accessible and then blah blah blah. Only in corollary C, you not see this. You not see this. Corollary C, you not assume the perturbation F to be accessible. I'm not sure if you missed that part or you don't need that.
Oh, we missed it. It's a typo.
Okay. Okay. And so my comments is about the theorem C and also theorem B and the corollary C is like the following. In order to get the rigidity, smoothness, differentiability, not only you assume M is two-dimensional, you need a key hypothesis is the exponent are the same with linear and also base. It's necessary. I mean, in theorem B, the Eaton 3, you said F is topologically conjugate.
Yes.
If we are trying to improve the topological conjugation to smooth, one important step is you need to assume the strong exponents, not only the center exponent to 0. You get the theorem B, C, Eaton is topological conjugation, you need to assume the center exponent to be vanishing, right?
Yes.
In order to improve, I think maybe it's necessary you assume the strong exponents are the same with F0.
What could you please repeat? What is
the strong stable and the strong unstable exponents are the same? Okay. Why? Because if you assume that, then you could prove that it's easy. The center foliation are smooth. The center foliation is smooth. Okay, so it's smooth conjugated to skew-product already. And then you only need to consider the WX is smooth or not with respect to the base. Okay, I think this should be true. So then you can write a corollary like a more beautiful thing, stuff like the rigidity. This is really smooth rigidity given by the exponents. So a correct result should be, okay, I'm not sure, but I think it should be true if any perturbation of F0, if it's accessible, and if all these exponents of F0 coincide with F, then you have smooth conjugacy.
Okay.
Or just the comments. Maybe this should be correct.
Okay. So we'll talk more about this.
Yeah, and my another comments is about the assumption about the accessibility, because we know that you know the three-dimensional near manifold, the Heisenberg group, because in three-dimensional near manifold Heisenberg group, it's a near manifold, not a T3. Any partial body diffeomorphisms on near three-dimensional near manifold different to T3 is accessible. Okay, and Marcel also, so it's possible you should consider not a skew-product. I mean some examples. It's not a skew-product, but with some near manifold, right? Near manifold on the fiber, and maybe this will give you accessibility directly. I think this soluble this kind of problem for a couple of years, but definitely there should exist some examples. It's a near manifold, not a skew-product, okay? Manifold, not a skew-product. And it's a kind of bundle. You have two-dimensional bundle, but it's not trivial bundle. And I guess in most of the cases, you should have the accessibility directly. And Marcelo and Ahdouk, they proved the accessible is always open, so you can simplify more. You give some interesting example without any assumption about the accessibility. Yeah. Okay, and that's my comment. I like this paper very much. Yeah.
Thanks a lot.
Congratulations. Okay.
Thanks a lot. And I want to talk more about that comment you made about the equality of the Lyapunov exponents.
Okay, you should take a look about my paper with Radu. I had a joint paper with Radu Sakin, and there we show if the strong bundles are the same, strong exponents, strong stable, strong unstable exponents are the same, then the center position should be smooth. Okay, can put them to be vertical, and then you only need to consider your Wx, your function, is depends smoothly on the base. I guess that should be true. And then you have a much interesting corollary. The exponents give you smooth conjugacy. That has been done by observed first, I think, by Marcelo and Arthur and Amy. Yeah.
Okay.
In some other case. Okay, that's my call. Yeah, congratulations.
Thank you.
Thank you very much again. Excellent points. Luna, passo a palavra para você agora.
Oi.
Olá.
Você prefere que fale em português ou em inglês? Não entendi nessa.
Em inglês, porque eu nunca cheguei a fazer matemática em português.
Okay,
um dia aprendo.
It's fine. Don't worry. None of them is my mother tongue, so
Yeah.
I really don't care.
Indeed.
First of all, congratulations.
Thank you.
It's a very nice thesis with very nice results. I must admit that when I got the invitation, a part of me reading partially hyperbolic felt a little bit, it's not exactly what I... But actually all this, the conformal structure and the Riemann metric and all of this, it felt very, very, very nice because it could very much connect it from what I do. So I liked it very much to read your thesis. And thank you for the opportunity, really. Say this, I agree very much with Karina. What is written is very well written, but there are some parts that you could write more thoroughly. I mean, if you look in your thesis, you defined F0 to be G0 on the first coordinate and gamma x mu, and you don't say who is gamma. There are several things that are very important that are not written down. You use a lot of results saying about your theorem this in this book, and it's a little bit heavy going to search everything, and being a thesis, a nice thesis, and thesis can be written, read by other students. It would be very nice if you could, how you say, develop a little bit the material by putting more introductory things, stating the results you state, you use, and all of this, because I felt a little bit a lack of this. This said, let me understand, for proving your theorem B, what you do is that well, theorem A in the third case gives you a conformal structure on EC, ECQ for every Q, and it's continuous. And then what you do is integrating it by measurable Riemann mapping theorem. Is this that you do, right?
Yes.
Okay. Hence, I start agreeing with Karina on the fact that if you drop the hypothesis that your map is symplectic, you will just have the conformal structure. So you won't have the Riemannian metric, but you can still integrate your conformal structure. So maybe you could consider studying restricting yourself to some kind of family you know better, or I don't know, and dropping the symplectic statement, developing a bit theorem B, saying, okay, if theorem B and theorem D, which are in the same spirit, in the sense you are integrating conformal structures in both ways. And maybe you could think, okay, if I drop a symplectic and I keep integrated structure, what can I get? Just a suggestion.
Okay.
And speaking about that, to me, it wasn't very clear how you know that your almost complex structure is uniformly bounded. Because for using the measurable Riemann mapping theorem, you need to know that the essential supremum of the Beltrami coefficient is less or equal k less than 1. And I didn't really find this. So how you know this?
It's continuous. It's
okay.
continuous on a compact space.
Okay, so it has to be. Okay, thank you. What else I wanted to say? Another comment was, if you try to drop accessible instead, then you're stopped from the starting point because you cannot using the disintegration. You don't get the whole manifold, right?
Yes, yes.
So you couldn't try to go on those
No,
sides. It doesn't
no.
really make sense. Okay.
No.
Okay. Okay, these were, well, then I had other questions or comments that has been stolen before. So I will stop here, but it was very nice thesis, nice presentation. So congratulations.
Thank you.
Muito obrigado, Luna. Nós sofremos bocado para provar a continuidade da estrutura conforme, por isso mesmo.
Sim.
Deu bocado de trabalho isso aí.
Não, tá.
Você usa o teorema mensurável de Riemann, mas precisa fazer isso de maneira mais explícita, mais detalhada, para poder dizer, olha só, o resultado é contínuo.
Sim. Mas talvez seria bom comentá-lo no texto.
Sim.
Porque...
Com toda a razão. Khadim.
Okay. First of all, thank you for the invitation in the committee. So I have an excuse to speak. It was in English, so I'm going to speak.
Sure. So your audio is low.
Oh. Are you hearing me?
It's okay.
Better.
Okay. Yes, so first of all, congratulations, Sankhadip, for this nice presentation and also for the nice results. I really enjoy reading the thesis. It's a very nice result. I always like to see the results from the dynamics. We did some topology, we recover some structure.
You're cutting in the middle sometimes.
Why is that? I'm sorry, I don't know what is that. So I was just saying that I like this type of result that you have the rigidity result that from the dynamics you recover the topology and also the geometry sometimes. So the questions I was having, like one of them is a little bit, on the opposite side, that people were talking about dropping symplectic. But so far for me, I would like to keep symplectic. My question would be how, would you need, which is related to what Karina was saying about the skew-product, to start with the skew-product. Like in theorem A, do you need the fact that you have a perturbation of the skew-product, or you could just do something with dynamically coherent symplectic and accessibility and stuff?
Khadim, your audio was very cut. I think at the end we understood you were asking whether we need skew products to begin with.
Yes.
In the context of theorem A.
Yes.
Yeah. Yes. So I think, Sankhadip, the answer is probably no.
Well, if we drop the skew product, then we have to discuss more about the question of getting a model of the center manifold. So we have a model which is S, and then we discuss what S could be and could not be.
But we could start. We could probably. We didn't think about it honestly. I think since theorem A actually came after the other ones, it was probably contaminated in terms of statement by theorem B. We could probably think of a system still Fibred. Fiber essentially forms a fiber bundle whose model fiber is S, but it's not necessarily a trivial bundle. The fact that it's a trivial bundle and the foliation itself is we start with is smooth is I don't think it's used at all.
Yeah, my question was related because this type of questions also they belong to this classification of partial hyperbolic. It's very known in 3 dimensions. We know exactly what is happening. And to start already in dimension 4, putting symplectic is a good condition to start with. So I think it's very good to understand. And it is also related to one thing I was thinking about with you and Khadim about when you get into the coherence dimension 4 when you put symplectic. So that's a good question. So the second question would be about theorem A number 2, theorem A2. Do you have that those 2 conditions, those 2 things, like those 2 things are not empty? Like you said that you have either a line bundle, an invariant line bundle, or you have 2 invariant line bundles. Do you have an example where you have only one?
There is one in the paper, right? There one.
So I probably, yeah.
Yeah, that's okay. Let me check where it is. Yeah, so it's example 6.2.
Okay, I will check it. Okay, I'm okay with that. So maybe the last question would be about you see the proof of the fact that the holonomies are symplectic.
Okay.
Is that is general, like for partial hyperbolic, or it just need to be a perturbation of the skew-product, like the fact that the holonomies are symplectic?
We actually use the perturbation thing.
You use the fact that you have a skew-product, or
Let me check really quick. I think we just use that the central. Just a moment.
There's one way in which we use it is to guarantee that dynamical coherence is preserved. Okay, but again, it's a very mild use of the fact that the unperturbed map is a skew-product. Skew-products, you can use the theorem of Hirsch-Pilk-Schuh about Blake expansiveness, about stability of center foliations.
okay,
But
okay,
that's not really an answer to your question. We could instead say we start with any map with the right properties, as Karina suggested, including stable dynamical coherence. It would be more general.
Yeah. Okay. Yeah, I have also 2 typos. Maybe I will send them to your email. Yeah.
Okay.
Yes, please do.
Congratulations again.
Thank you.
Thank you, Khadim, for your availability for the committee. Thank you, everybody. It was a good presentation, Sankhadip. I'm going now to invite you to leave the conference room. And also, I ask Anderson, quero pedir para suspender agora a transmissão.
Tá bom.
Bom, mais uma vez, boa tarde a todos. Estamos de volta à transmissão ao vivo para o YouTube da defesa de tese do Sankhadip. Nesse interregno, a Banca deliberou, avaliou a apresentação, o conteúdo da tese, e eu tenho o prazer, Sankhadip, de parabenizar o mais recente doutor pelo IMPA. Parabéns em nome de todos nós. Você quer dizer alguma coisa para encerrar? Você está com o microfone mutado.
Sorry. I would like to thank all of you for taking the time to go through my thesis and giving me all the suggestions. And I would like to thank especially Marcelo, because it has been a difficult year for all of us, right? And it was hard, and he was always by my side. So thank you. Thanks a lot.
This has been a tough couple of years with
yes.
procedures for interacting. Hopefully next year we'll be back person, and we'll still have transmissions online broadcasts of the defenses, but we can meet in person and even have some sort of social interaction, as was requested, by the way, by some of the committee members when we were not live. Gente, muito obrigado a todos. Obrigado de modo muito especial aos membros da banca pela disponibilidade, pelos comentários, que foram excelentes. Eu quero aproveitar também para agradecer ao pessoal da coordenação de ensino, Isabel, Dui, e da coordenação científica do IMPA, Anderson, conduzindo essa defesa. E parabenizando o Sankhadip, avisá-lo que a partir daqui é que fica difícil. Até aqui foi kindergarten, agora é que a vida começa para valer.
Estou entendendo. Já tô percebendo.
Faço votos de muito sucesso na sua carreira. Um abraço a todos, gente. Boa tarde.
Parabéns, boa tarde.